Welcome to Day 12, Double Angle Formulas. You will need the 3 P's, paper, pencil, patience. You will also need a graphing calculator. Today, we will talk about the double angle and Pythagorean theorem substitutions when it comes to utilizing trig functions in equations. Double angles refer to a trig function that has the value of its angle doubled. For example, sine 2a or cosine 2a, which you will see on the reference sheet. However, more likely than not, you will utilize it utilizing sine 2 theta or cosine of 2 theta. On the reference sheet in the exam, there will be 4 double angle formulas given to you, but there are only 2 which rewrite a double angle function in terms of one function, and those are where we will focus our attention. The formulas that we will use and focus on are cosine 2a equal to 2 cosine squared a minus 1, and also cosine 2a equal to 1 minus sine squared a. If you notice, in both cases I have a double angle function that is being rewritten in terms of one function only. In the first case, I'm rewriting the double angle in terms of cosine, because I have a cosine squared term. In the second, I'm rewriting it in terms of sine, where I have a sine squared term. You should note that whenever you see a double angle, you will always replace it in order to simplify, and you will choose which formula to use based on which functions you have in your equations. The Pythagorean substitution involves our big papa equation, that is to say, sine squared theta plus cosine squared theta equals 1. As we saw in previous days, the consequences of this equation allow us to write a sine square function in terms of cosine squared and vice versa, as shown. As such, we can use these consequences to substitute in when we need to simplify or factor an equation that has multiple terms. In these problems, you should always look to substitute for the squared term. Now, let's practice a little bit with substitution. These are the 4 double angle equations you will be given on the reference sheet. Note that only 2 of them have a substitution that has only one function in it, so we will focus only on the bottom 2. In the first example, you note that we have a double angle and a second term that is in terms of sine. As such, we will choose to use the substitution that involves sine and rewrite our problem as shown. Similarly, with the second example, we have a double angle and a second function of cosine. So, we are going to choose to rewrite the double angle using the substitution that involves cosine. The substitution is as shown. Now, let's practice with a couple of examples. In example 1, we are told to solve for theta on the given interval. What I'm going to do is I'm going to start by rewriting my problem. Cosine 2 theta minus sine of theta is equal to 0. The first thing that I should note in this problem is that I have a double angle. I also note that the other function in the problem is sine of theta. So, what I'm going to do is choose to substitute my double angle with the substitution from my sheet that involves sine of theta. I'm going to place parentheses around the term I'm substituting and rewrite my equation in terms of the substituted value. Now, if you notice, I have a sine squared term and a sine term. The sine squared term has a negative value in front of it, so this means it's not quite in standard quadratic form. I can change this, though, by multiplying through both sides by a negative 1. This should give me a value of 2 sine squared theta minus sine of theta minus 1 equal to 0. Since I am set to 0 and now I'm in standard form, I can factor and solve. In this case, you could use funky factoring, but I'm going to suggest that you use the quadratic formula throughout all of your examples. And here's why. You might be able to use funky factoring, but you might not be. And if you use funky factoring and it doesn't quite come out right, you're going to have to use the quadratic formula anyway. To use the quadratic formula, find your a, b, and c. Write your quadratic formula out, negative b plus or minus the square root of b squared minus 4ac all over 2a, and plug in your values for a, b, and c. You should come out with two values for sine of theta. In this case, negative 1/2 equal to sine of theta, and 1 equal to the sine of theta. Since both cases are within the domain, rather the range of sine, we can proceed to solve the same way we did in days 10 and 11. For sine theta equal to negative 1/2, I should have a reference angle of 30 degrees and two values of theta in 3 and 4 as shown. Similarly, for sine theta equal to 1, I get a reference angle equal to my theta in 1, or simply 90 degrees. In example 2, I follow a similar process, except I note that I have a double angle and a second function of cosine. Therefore, to begin this problem, after I have rewritten it, I will substitute for the double angle using the value from my reference table that has cosine in the term for the value that I'm substituting in for. In this case, cosine 2a is equal to 2 cosine squared theta minus 1. I bring down my coefficient of 3 cosine 2 theta and substitute in the value that I have chosen from my reference table. Now, note that I am putting this in parentheses. This is to assure that when I am substituting, I'm substituting in for the correct term, and also that later on I distribute this 3 throughout to all of the terms that I'm substituting in for. So I'm going to distribute that 3 to the 2 cosine squared theta and get 6 cosine squared theta, and I'm also going to distribute that 3 to the negative 1, getting negative 3. I continue and write the remainder of my terms, plus cosine theta plus 5 equal to 0. Now I simply have to combine like terms, and I have my equation in standard quadratic form. Once again, I'm going to use the quadratic formula here, and I will get two values for the cosine of theta. In this case, I have the cosine of theta equal to negative 1.549. I also have a value of cosine theta equal to positive 0.2153. Remember that sine and cosine only have a range between negative 1 and positive 1, so I can reject my first value for cosine of theta and proceed to solve for the values of theta that will come out of cosine theta equal to positive 0.2153. I take the inverse cosine of both sides and get a reference angle of 78 degrees in quadrant 1 and 4 where cosine is positive. This tells me that my angles, which I can plug in for my original equation, will be theta in 1 equal to 78 degrees and theta in 4 equal to 282 degrees. Now are you ready? We're about to use the Big Papa substitutions. In example number 3, we are going to use the Pythagorean theorem substitutions. Remember, this is our Big Papa and its consequences. Note, you have an equation with a cosine squared term and a sine term. As such, we will use the consequence of our Big Papa and substitute in 1 minus sine squared theta for cosine squared theta, making sure to write parentheses around the substitution so we remember to distribute the coefficient of 2. After substitution, I can distribute the 2 throughout, and now I have two sides of the equation that have terms on them. Remember, to solve for the values of theta, I need to set this equation equal to 0. So I rewrite it so that I can place it in standard quadratic form, and I come out to an equation, or rather an expression, 2 sine squared theta plus sine of theta minus 1 is equal to 0. Now I'm in standard quadratic form, and I can use my quadratic formula. Once again, if I use the quadratic formula, I come out to two values for sine of theta. Sine theta equal to 1/2 gives a reference angle of 30 degrees in quadrant 1 and 2, giving you angle values of theta in 1 of 30 and theta in 2 of 150 degrees. Sine of theta equal to -1 will simply give you a theta in 3 equal to -270 degrees. In example 4, we have a sine squared term and a cosine term that follows. Once again, we will use the consequence of our Big Papa equation, substitute in for the squared function, and rewrite the equation in terms of one function of theta. Once again, remember to write parentheses around the term that you are substituting for, so that you remember that once you've substituted, you still need to distribute the coefficient. So here, substituting in 1 minus cosine squared theta for sine squared theta, we have that in parentheses, so we distribute the 4, and we get 4 cosine theta minus 4 cosine theta plus 1 equal to 0 once we have distributed, simplified, and rewritten in standard form. Once we have it in standard form, we can use our quadratic formula and get two values for cosine of theta equal to 1 plus or minus the square root of 2 all over 2. If I plug this statement into a calculator, 1 plus radical 2 over 2, I get a value of cosine of theta equal to 1.2071. But remember, this is outside of the range of cosine of theta, so I'm going to reject it. Bye-bye. If I take 1 minus radical 2 over 2, I should get cosine theta equal to -0.2071, and I can solve similar to day 10 and 11. I'll have a reference angle equal to 78 degrees in quadrant 2 and quadrant 3 because cosine, if you notice, is negative, and these are the quadrants where cosine is negative. Now, if you remember, we're told to solve for theta to the nearest degree, but we're also given an interval in radians. Well, if this happens, what you need to do is leave your answer in degrees. You do not leave it in radians. You don't have to transfer it because it's telling you to solve to the nearest degree. So there is no conversion necessary. So simply use your quadrant operations with your reference angle, and you should come out to a value of quadrant theta in 2 equal to 168 degrees, and theta in 3 equal to 258 degrees. So once again, to review, you're going to have the functions of the double angle given to you on the reference table. You also have your Big Papa equation, sine squared of theta plus cosine squared of theta is equal to 1, and the consequences that come out. The four functions of the double angle will be given to you on the reference table for the exam. You don't have to memorize them, but you do need to know how to use them, so practice with the substitutions. Your Big Papas are not given, so fair warning, memorize it, memorize it, memorize it. You have been warned. Here are the skills that you should be able to do. If you're having trouble with any of these, go back and re-watch the video focusing on the skill that you're struggling with. Until next time, this is Mr. Mackman signing off.